In this video, we're going to look at angled projectiles and calculate all the properties for an object that is launched at an angle, moves up in the air, and then falls back down in this parabolic path. To start us off, let's review some of the mathematical skills that we know about. We know how to split up an angled vector into its horizontal and vertical components using trigonometry, SOHCAHTOA. We also know how to use our SUVAT variables and the kinematic equations to solve for an object that is moving at a constant acceleration, basically something that's moving like acceleration of gravity. Now, for our warm up, you launch a ball up in the air at 19.7 meters per second. How high will it go? How long will it be in the air? Well, we know that the initial velocity is 19.7 meters per second. If I want to know a final velocity, it's helpful for us to be able to access the highest point. We know at its highest point in the trajectory going up in the air, our final velocity is going to be zero. It comes to a stop for a split second before it turns around. And then due to gravity, our acceleration is negative 9.8 meters per second squared. We're defining down as being negative so that up, our initial velocity is positive. Now, how high will it go will be our displacement, which means we don't know the time. Our kinematic equation that doesn't use time is v squared is equal to u squared plus 2as. Plugging in the variables that we already know about, we can solve for s to be 19.8 meters. Okay, then how long will it be in the air? That is a time. I have every other variable except for time, so I'm just going to use the kinematic equation that's easiest. I think it is v is equal to u plus at. I know what v and u and a are. I can solve for t. T is 2.01 seconds. But that doesn't actually answer my question. My question was how long will it be in the air? Remember, in order to call the final velocity zero, we are looking just at the first half of the problem. So we need to multiply that by 2 to find the airtime. So airtime is 0 or 2.01 times 2 or 4.02 to go up and then back down. All right, we will see that again later on. But first, let's remember some things about vectors. If I have an initial velocity of 24 meters per second, that's at an angle of 55 degrees. I know that part of that velocity is horizontal, we'll call that ux, and part of that velocity is vertical, we'll call that uy. This makes a triangle of the horizontal and vertical parts and our angle of 55. If I want to solve for each of these, u is attached to the angle, that is my adjacent side, so it's going to go along with cosine. 24 times the cosine of 55 is 13.8 meters per second. The y is the opposite side, 24 times the sine, opposite over adjacent, opposite over hypotenuse rather, sine of 55 is equal to 19.7. So 19.7 is my vertical, my uy. So remember, when we were talking about a projectile, it is helpful for us to split the projectile up into two distinct components. We have a vertical part that is accelerating. So if I throw an object in the air, it slows to a stop, turns around, and then speeds up going down. If I roll an object on the ground with no friction, it is moving at a constant velocity the entire time. So we're going to say that vertical is accelerating, horizontal is a constant velocity. Vertical, we'll use our kinematic equations and SUVAT the entire time. Horizontal, we're going to stick to this constant velocity equation of distance divided by time because there is no acceleration. Well, acceleration is zero. Let's see that again. If I take these motions and I combine them, we now get a projectile that is moving in this parabolic path. A couple things to note. This horizontal component, that light blue vector, is always the same. And this dark blue vector is going up but slowing down and then going down and speeding up, just like an object that were thrown up in the air. If I combine those two, we get the hypotenuse of a triangle with those two vectors as the sides, and we see this angle that traces this parabolic path. Just to note that the second half of this is the same as a horizontal projectile. That's something that we saw in the last video, where something were launched perfectly horizontally. Now we're just going to look at the entire thing. It will eventually get to that same horizontal up at the top, but we're going to start before that point. So let's look at the first half of a projectile with that same triangle that we saw earlier. We said that the vertical component of this 24 meter per second vector is 19.7 and the horizontal is 13.8. If I'm looking at the first half, but just the vertical part, I need to be paying attention to what's happening vertically. Vertically here at the top, I have a final velocity of 0, just like if I throw something up in the air. Vertically or horizontally at the top, I have a final velocity that is exactly the same as the velocity I calculated initially as the horizontal. 13.8 meters per second horizontally is always 13.8 meters per second. So at the top, when it's all horizontal, that is what I have. So let's look at the first half vertical. I know that I'm starting with an initial velocity vertically of 19.7. I'm not putting the 24 in, even though that is my overall initial velocity. I am splitting this up just to be the vertical components. My final vertical velocity is 0 at its highest point, and my acceleration is negative 9.8. Now, we've actually seen this. This was the exact same problem that we saw before. Our time was 2.01 and our height is 19.8. Those are the same values that we saw for an object launched straight up in the air at 19.7 meters per second because its vertical motion actually matches that of the vertical components. Now, if I want to look at the full thing, so look at the horizontal part of this as well, I know that it travels in a horizontal direction and it has a time that it's in the air. Well, the first half to get to the top, we said was 2.01 seconds, which means that the total time, as we did before, is double that, 4.02 seconds. The displacement is based on how far it can go in that amount of time. We know what the horizontal velocity is. And the distance that it can travel at a constant velocity is just the velocity times the time. The horizontal velocity started out at 13.8 and it continues at 13.8 the entire time. So we'll say 13.8 meters per second times the total time it's in the air, 4.2 seconds. It will be able to cover 55.5 meters roughly. Now, again, that is just how far it can go horizontally in the time that it's airborne, and we know how long it's airborne based on its vertical components and the SUVAT equations that we calculated earlier. So in general, here are a couple things that we know about a horizontal or an angled projectile here. We know that it starts with some velocity u that's at an angle and it traces its parabolic path. Well, that angled u can be split up into a ux and a uy, horizontal and a vertical component. Now, if we're looking just at the first half, my acceleration vertically is always going to be negative 9.8. U is always going to be that y component of the initial velocity. So once I do my triangle, and then my final in the vertical is just going to be 0. And then here we also know that the horizontal part of the vertical is going to be equal, or horizontal part of this final spot is going to be equal to whatever that initial horizontal was from my original triangle. Then the vertical displacement here, S, is essentially your total height. So how high it goes, because you're looking at the first half. And then T is just half the time. So the total time is 2 times whatever that T is. And the displacement in the X direction is UX, so the initial X part of that triangle, times the total time that it's in the air. All right, so let's look at a couple conceptual things and then we'll do all of this at once with one final example problem. So if I have two objects here, or two different trajectories for a single object, A goes up really high, lands in a spot. B goes up not as high, but lands in the same spot. Actually, it turns out there's two different angles that will land in that same location, reflected around 45 degrees. Which one's going to land first? Well, if I look at this and I actually animate it, we'll see that B lands before A does. The time is based entirely on how high it goes. The higher it goes in the air, the longer it's going to be airborne because the timing will match essentially an object that's thrown straight up, going to the same height. So the higher it goes, the more time it's in the air. See another example. What if I change their trajectories? They don't land in the same spot anymore. A doesn't go as far. B goes farther. Well, you'll see here we still follow the same rule. The higher it goes, the longer it's in the air. So B lands first. Even though it goes farther, If it's shot at a lower trajectory angle, it is not going to go as high. Because of that, it is not in the air as long. So only the vertical velocity and height affect the airtime. All right, let's look at one final example, solving for everything. You hit a baseball at 24 degrees above the horizontal at a speed of 30 meters per second. How far does the baseball travel before it hits the ground? The first thing you should do anytime you're solving a projectile, if you know a speed and an angle, you should calculate the horizontal and vertical components. So my horizontal, the x, is 30 times the cosine of 24, because that is the adjacent side. That's 27.4. The y, the vertical component, is 30 times the sine of 24, or 12.2 meters per second. Now, my final x, so the highest point here, the x velocity is still that 27.4 meters per second. And then my final in the y, for the highest point, is 0. Now, let's start putting things into our structure here. We know that the acceleration in the vertical is going to be negative 9.8 meters per second. Now, we know that the initial vertical direction velocity is 12.2. That's what we calculated here as our vertical part of the triangle. And then the final velocity in the vertical part at the highest point is 0. From that, I can solve for the time. V is equal to u plus at. Plugging in my 12.2 and my negative 9.8, I can find that the time is 1.24 seconds. That is the time, again, to get to the highest point. I could also, just for fun, calculate how high it goes. That is 7.56 meters. That's not actually explicitly called for here because I'm only asking how far does the ball travel before it hits the ground. I don't need to know its height, but that's how you'd find it. So you would find it in that first half of the vertical. Then I need to shift gears and look at the horizontal part. I know that in the horizontal direction, the total time that it's in the air is double whatever that first half was. So 2 times 1.24 is 2.48 seconds, and it has 2.48 seconds in the air before it lands. I know how fast it's moving horizontally during that time, so I can solve for the distance. It's just velocity times time. That's rearranging v is equal to d over t. The horizontal velocity is 27.4. The time that it's in the air total is 2.48. So the total distance that it covers is 68 meters. Now there's a lot there, but as a reminder, we can use this triangle to figure out our horizontal and vertical. We can use that vertical initial to figure out how long it's in the air. We can double that and multiply it by the horizontal velocity to figure out how far it goes. All right, with all of this, you should be able to calculate that horizontal and vertical component of the angled velocity. You should also be able to calculate the maximum height and the total air time for a projectile launched at an angle, and then ultimately use all of that to figure out how far it goes for that projectile launched at a certain angle.